In this video, we will look at the concept of work as it relates to electrostatic forces and electrostatic potential energy. Let us start with two charges that are infinitely far apart. When they are infinitely far apart, they cannot feel the field from each other, and so there is no interaction between them. What we will do is move one of the charges from infinity to a final distance RF. The other charge remains at the origin. From our earlier course, we know that the work done is integral dW, which can be written as the integral of f dot dl, moving from infinity to R final. In this case, Fe is the force that the charge at the origin exerts on the moving charge, and dl we have written in polar coordinates. Notice that since we are looking at the force that one charge exerts on the other through the electric field, we say that this is the work done by the electric field. Alright, so let's plug in Fe and dl. And when we do the dot product, we notice that r hat dot theta hat is 0, so that disappears, and r hat dot r hat is 1, and so we are left with dw is equal to kqq dr over r squared. Now we want the total work, so we integrate this result. The integral of 1 over r squared is negative 1 over r, and we evaluate at the limits. Now, 1 over infinity is technically not defined, but we're physicists, so we'll call it 0. So our final result is, if we have one charge, capital Q, at the origin, and we move the other charge, little q, from infinity to a final distance RF, then the work done is minus QQ over RF. This is the work done by the electric field, not the work done by us. Why is this work negative? Well, let's take a look. As we move the little green charge, we can move it in any path we want. It doesn't have to be straight along the r hat direction. We can move it like this, as long as we eventually start from infinity and end at RF. Now, the electric force on this little charge always points directly away from the charge at the origin. dl, as we said, could point in many different directions. Theta is the angle between them that we took into account when we did the dot product. But in the process of moving from infinity to RF, overall dl is pointed to the left and Fe is pointed to the right. Since they point in opposite directions, the work done by the electric force, and thus the work done by the electric field, is negative. Since we are pushing it overall in the same direction that it is moving, mostly the work done by us will be positive. The exact value, however, depends upon, does the charge gain kinetic energy or lose kinetic energy? And so to find the work done by us, we need some more information. But the work done by the electric field is just given by that final expression, minus kqq over r final. Notice that this is assuming that the two charges have the same sign and are repelling each other. If they have opposite signs and are attracting each other, then the electric force will point to the left, and so will the movement of the charge. In that case, the work done by the electric field is positive, and the work that we do will usually end up being negative. The electric force is another example of what we call a conservative force. This means that the work done by the electric field is independent of the path taken. It only depends on the starting position and the ending position. We also know from our earlier course that for every conservative force, there is an associated potential energy. The relation that we found was that the work done by a conservative force in moving from an initial position to a final position was equal to minus delta U, where U was the associated potential energy. Let's apply it to this case. Here we are looking at the work done by the conservative electric force as we move the charge from infinity to RF. We have calculated that amount, and so let us set it equal to minus delta U. That is minus bracket U final minus U initial. If we set the potential energy at infinity equal to 0, which makes sense because the charges can't feel each other, then we arrive at negative U final equals negative KQQ over RF. Or in other words, the potential energy is a function of the separation between the two charges and is given by KQQ over R. Notice that if both the charges are positive or if both the charges are negative, then the potential energy is positive. So if the charges repel each other, then the potential energy is positive. But if the charges have opposite signs, then the potential energy is negative. Here is our first example question. The potential energy of the system in configuration 1 is negative 4 joules. What is the energy in configuration 2? Pause the video and try and think of the answer by yourself. We now discuss the answer. Alright, the energy in configuration 1 is negative 4 joules. What has happened as we change from configuration 1 to configuration 2? The distance has doubled. But we know that the potential energy is inversely proportional to the distance. So if the distance is doubled, the energy should be halved. So the final energy is negative 2 joules. Here's another example question. The potential energy of the system in configuration shown below is negative 4 joules. Are the charges the same sign or opposite signs? Pause the video and think for a moment. We now discuss the answer. Since U is negative, but K and R are always positive, this means that QQ is negative. In this case, Q1 times Q2. So that means that one of them must be of the opposite sign to the other. Here is a third example question. Here, both charges have the same sign. We move the system from configuration 1 to configuration 2. And the question is, does the electric field do positive work or negative work? Pause the video and think of the answer. We now discuss the answer. In moving from configuration 1 to configuration 2, we can see that DL is to the right. And we also see that since the two charges have the same sign, they repel one another. So FE is also pointing to the right. Since both FE and DO point in the same direction, the work done by the electric field is positive. Now, if the charges start and end at rest, then the change in kinetic energy is 0. We know from the work energy theorem that the total work done on the system is equal to the change in kinetic energy. If the total work done on the system is 0 and the work done by the electric field is positive, then that means that the work that we do on the system must be negative. Here is another example question. An electron moves in a circle around a proton as shown. So it's going to start here and move in a circular path to here. And the question is, what is the sign of the work done by the electric field on the electron? And is the electron faster or slower when it reaches the finish point? Pause the video and think of the answer. We now discuss the answer. The velocity is always tangent to the circle. The electric force is pointed inward along the radius, and so the angle between the displacement and the force is 90 degrees. Since they are perpendicular, the work done by the electric force is zero. Since this is the only force acting on the electron, and the work that it does is zero, then the change in kinetic energy will also be zero. And so the electron has the same speed when it reaches the finish point. The direction of the velocity is different, but the magnitude is not. Let us now look at how we can explain attraction and repulsion in terms of energy. Consider two positive charges, a plus 5 Coulomb charge and a plus 2 Coulomb charge. The system has some electrostatic potential energy. But we know that if we release a system from rest, then it will try and act to decrease its potential energy. Will that happen if the charges move closer together or move further apart? Well, since both the charges are positive, the potential energy is positive. So decreasing the potential energy means becoming less positive. Since the charges can't change the value of the charges, they can only change the distance between them. Increasing the distance between them will make the potential energy less positive, which is decreasing the potential energy. And so the system tries to move apart. But this makes sense. Positive charges repel each other. So we can explain or describe the repulsion between two positive charges also in terms of the energy that the system has. What about a positive charge and a negative charge? Here, the potential energy of the system is negative. And we want the potential energy to decrease. In this case, that means to become more negative. Remember, we think of positive numbers as being higher than 0, and then negative numbers as being lower. So the more negative the energy, the lower it is. In order for the potential energy to become more negative, we want the distance between the charges to decrease. As it does so, the potential energy becomes more negative. And so we explain attraction between opposite charges in terms of energy. Finally, how do we discuss the potential energy of a system of many charges? Here's an example. We have 4 different charges, 3 of them positive, 1 of them negative, and the distances between each pair have been specified. How do we calculate the potential energy? It turns out that the total potential energy is found by getting the potential energy of each pair of charges. In this case, with the 4 charges, there are 6 different pairs. I have labeled the charges A, B, C, and D. The pairs are AB, AC, AD, BC, BD, and CD. We plug in the formula for each of them and calculate the numerical values. And in this case, the final total potential energy is about 65.5 joules. That's the end of this video. I'll see you in the next.